Something is happening beneath the Pacific Ocean, and the scientists who study it most closely are choosing their words very carefully. In the past several months, a stretch of seafloor running along the western edge of the United States and up through Alaska has been shaking in ways that do not follow the normal patterns. Hundreds of small earthquakes, clustered together, firing off in sequences that seismologists call swarms. Not one big event followed by aftershocks, swarms, which is a different thing entirely, and the difference matters more than most people realize. The United States Geological Survey issues updates. They post the data publicly. They are not hiding the earthquakes themselves, but there is a gap between what the raw data shows and what gets said plainly in a press release, and that gap is where the real story lives. Because when you look at where these swarms are concentrated, and when you understand what sits beneath those specific locations, the picture that forms is one the agency cannot officially state without triggering a level of public alarm it is not prepared to manage. So let us talk about what the data actually shows. Let us talk about what lives beneath the Pacific floor along this particular arc of the planet. And let us talk about why a pattern of small earthquakes, when they appear in the right place and in the right sequence, can mean something far more significant than the size of any individual quake might suggest. To understand why this swarm is unusual, you need to understand what the Pacific is, not just as a body of water, but as a geological system. The Pacific Ocean sits on top of what is essentially a massive engine of destruction and creation running simultaneously. Tectonic plates are grinding, diving, and in some places being born at a rate that makes the surface of this planet feel genuinely unstable once you start looking at the timescales involved. The eastern edge of the Pacific is where the Juan de Fuca Plate meets the North American Plate. This boundary runs from Northern California up through Oregon, Washington, and into British Columbia. It is a subduction zone, which means one plate is diving underneath the other. The Juan de Fuca Plate is being swallowed by the continent at roughly 45 millimeters per year. That is not very fast by human standards. By geological standards, it is relentless. This system has a name, the Cascadia Subduction Zone. And if you have spent any time reading about Pacific Northwest geology, you already know that name carries weight. Because this subduction zone has produced some of the largest earthquakes in the recorded history of the North American continent. The last truly massive rupture along the Cascadia system happened in January of 1700, and the evidence for what it was and what it did is written into the ground itself. Trees drowned in sudden coastal flooding, sediment layers bearing the fingerprints of catastrophic shaking, indigenous oral histories describing the earth moving and the sea coming inland, and the Japanese tsunami records, which logged a wave arriving on their coastline from an unknown source on the other side of the ocean, on a night when no local earthquake had been felt. The scientists who have reconstructed that event estimate it produced a magnitude 9 or greater earthquake. The shaking would have lasted several minutes. The tsunami that followed would have reached heights in some coastal inlets that are difficult to fully comprehend, and the Cascadia subduction zone is still there, still locked, still accumulating stress. The Juan de Fuca Plate is still diving. The two plates are pressing against each other along a contact zone that stretches for nearly 1,000 kilometers. The question that has occupied Pacific Northwest seismologists for decades is not whether another great rupture will occur, it is when. Now here is where the current swarm becomes relevant. Earthquake swarms near subduction zones are not automatically a sign that a great rupture is coming. That needs to be said clearly. Most swarms decay without producing a major event. They're often associated with fluids moving through rock, with small adjustments along secondary faults, with volcanic activity that has no immediate surface expression. The Earth is restless in ways that do not always escalate. But some swarms are different. Some swarms are what seismologists call foreshock sequences, meaning they precede a larger event. The problem is that you cannot tell the difference in real time. The tools do not exist yet to look at a swarm as it is happening and determine with confidence whether it is a harmless tremor cluster or the opening act of something much bigger. This is not a failure of science. It is a fundamental limitation of the current state of understanding about how faults behave immediately before they fail. This is what makes the current Pacific swarm worth paying attention to. The clusters being recorded are not uniformly distributed along the coast. They're concentrated in specific zones that correspond to areas where the locked interface between the Juan de Fuca and North American plates is under the highest levels of stress accumulation. The geometry of the subduction zone means that stress does not build evenly. Certain segments of the locked contact surface are more fully coupled, meaning they move together and accumulate more elastic strain per year. When those segments eventually slip, they produce more of the total earthquake energy than other sections. The current swarm activity is showing elevated rates in some of those high coupling zones. There is also something else happening offshore that rarely gets discussed in mainstream coverage. Along certain segments of the Cascadia margin, scientists have identified a phenomenon called episodic tremor and slip. This is a slow-motion type of fault movement that happens at depths below where the typical locked zone ends. The plates slide past each other very slowly over days or weeks, generating what is called non-volcanic tremor, a kind of seismic humming that cannot be felt at the surface but can be detected with sensitive instruments. Episodic tremor and slip events have been occurring along Cascadia for as long as scientists have had the instruments to detect them, roughly since the early 2000s. They repeat on a relatively consistent cycle in different segments of the zone. But researchers have noted that tremor episodes and slow slip events effectively transfer stress. When the deep part of the fault creeps, the stress that cannot be released by creeping has to go somewhere, and it goes up, into the shallower locked portion of the fault, the portion that eventually produces great earthquakes. This is the mechanism that some researchers believe could act as a trigger, not a guarantee, a mechanism, a way in which the slow, quiet movements happening at depth interact with the fully locked, stress-loaded section above. When you overlay the current earthquake swarm locations with the zones where slow slip events have recently occurred, the spatial correspondence is notable. Whether that correspondence is meaningful or coincidental is something seismologists are actively debating. What is not debated is that the correspondence exists. Now let us move further north, because Cascadia is not the only system showing unusual activity. The Alaska Aleutian subduction zone is one of the most seismically active places on the planet. The Pacific Plate is diving beneath the North American Plate along a curve that sweeps from the Gulf of Alaska out through the Aleutian Island chain, running for over 3,000 kilometers. This system has produced some of the most powerful earthquakes in recorded history, including the 1964 Great Alaska Earthquake, which at magnitude 9.2 was the second largest earthquake ever measured by modern instruments anywhere in the world. The Aleutians have always been active. Swarms there are common, but the current activity includes clusters in several locations that sit above known volcanic systems, and this is where the geological complexity increases in ways that are genuinely difficult to communicate simply. Subduction zones produce volcanoes. As the diving plate descends into the hot mantle, it releases water from the minerals in its rock. That water lowers the melting point of the surrounding mantle material, generating magma that rises toward the surface. The volcanoes of the Aleutian chain and the Cascade volcanoes of the Pacific Northwest, including Mount Rainier, Mount Hood, Mount Shasta, and the others, are all products of this same process. A swarm of earthquakes near a subduction zone can therefore mean two very different things. It can indicate stress changes on the main fault interface, or it can indicate movement of magma within the volcanic plumbing systems that the subduction process feeds. Distinguishing between these two sources of seismicity requires very careful analysis of the waveforms produced by individual earthquakes, their depths, their spatial patterns over time. It is not always straightforward, and in some cases the two processes may be interacting with each other in ways that are only partially understood. In at least two locations along the current swarm zone, the earthquake depths and waveform characteristics are consistent with fluid migration, which could be hydrothermal fluid, volcanic fluid, or water released from the subducting plate itself. All of these processes can generate swarms. All of them produce similar seismic signatures. Separating them requires the kind of sustained analysis that does not produce results on the timeline of a news cycle. This is part of why public communication about these events tends to be muted. The honest answer to the question of what exactly is happening is, we are working on it, and we will know more in weeks or months than we know right now. That answer does not satisfy the public desire for clarity. But it is the accurate one. There is a deeper issue here, though, that goes beyond the technical complexity of interpreting swarm data. The Cascadia subduction zone presents a specific communication challenge that emergency management professionals and seismologists have been wrestling with for years. The challenge is this. The scientific evidence strongly indicates that a great earthquake on Cascadia is not a remote possibility. The geological record shows that this system produces great ruptures on a recurrence interval of roughly 200 to 500 years, with significant variability depending on which segment of the zone you're looking at. The last full margin rupture was in 1700. That is over 300 years ago. The system is, by any reasonable interpretation of the geological evidence, within the window for another great rupture. The Pacific Northwest has spent the intervening 300 years building cities. Portland, Seattle, Tacoma, Victoria, Vancouver, coastal communities along the Oregon and Washington coast, critical infrastructure, including ports, bridges, hospitals and pipelines, much of which was built before the scientific community fully understood what the Cascadia subduction zone was or what it was capable of. In 2015, a widely read article in a major American magazine described the specific risks of a Cascadia rupture in detail, and the piece created a genuine moment of public awareness. People talked about it. Emergency managers received calls, and then, as tends to happen, the immediate concern faded. Preparation efforts moved forward slowly, and the public attention moved on. The infrastructure vulnerabilities that existed in 2015 largely still exist. Preparation has improved in important ways, but the gap between the scale of what a full Cascadia rupture would produce and the current level of regional readiness remains significant. Emergency managers who work on this problem know it. The research community knows it, and communicating a heightened sense of urgency without specific evidence that a rupture is imminent is extraordinarily difficult in a media environment that cycles through stories quickly. This is the context in which earthquake swarm data gets communicated carefully. There is no conspiracy. There is no deliberate suppression of information. There is something more mundane and in some ways more frustrating. The genuine difficulty of translating probabilistic, uncertain, ongoing scientific analysis into public communication that is accurate, calibrated, and useful rather than paralyzing. When the United States Geological Survey issues a statement saying that an earthquake swarm does not indicate an increased probability of a major event in the near future, they are being technically accurate based on current understanding. They are also communicating in a way that does not convey the full texture of scientific uncertainty about swarm behavior. Both things are true at once. Let us talk about what the actual risk landscape looks like for the Pacific Northwest right now. The probability of a magnitude 8 or greater earthquake on the Cascadia subduction zone in the next 50 years is estimated by most researchers at somewhere between 10 and 15% for a full margin rupture. That estimate has wide uncertainty bands. For a partial rupture involving the southern section of the zone, the probability estimates are higher. These are not trivial numbers. A 10 to 15% chance of a major earthquake in 50 years is roughly comparable to the probability of drawing a specific card from a well-shuffled deck of cards, except the stakes of drawing that card are not a card game. They are the disruption of one of the most economically significant regions of North America. The shaking from a full Cascadia rupture would last several minutes. The area of intense shaking would cover a region stretching from northern California to southern British Columbia, with a total area comparable to the size of Japan. The tsunami generated by the seafloor displacement would reach some coastal communities within 15 to 20 minutes after the shaking stops. In some locations, the wave heights could exceed 15 meters. Coastal communities that sit on low-lying ground between the shoreline and the surrounding hills would have very little time to reach high ground on foot. For communities inland, the shaking itself is the primary risk. Liquefaction of saturated soils could damage or destroy buildings, roads and utility lines across a wide swath of the Willamette Valley and Puget Sound regions. Bridges along Interstate 5, the primary north-south corridor through the Pacific Northwest, are known to be vulnerable. The transportation disruptions following a major Cascadia event would affect emergency response, supply chains, and recovery operations for a period measured in months rather than weeks. None of this is secret. All of it is publicly available in reports produced by state emergency management agencies, university research groups, and the Federal Emergency Management Agency. The information exists. The question is whether it reaches people in a form that motivates action rather than simply generating anxiety. Now let us return to the current swarm and what it may or may not be telling us. The honest scientific position right now is one of heightened observational interest rather than elevated alarm. The swarm is being watched closely. The data is being collected and analysed. Researchers are looking at whether the current activity represents a meaningful change in the stress state of the subduction system or a transient cluster that will decay without consequence. That analysis takes time. There are some specific signals that seismologists consider potentially informative when watching a subduction zone swarm. One is the migration of earthquake epicenters over time. If the locations of swarm earthquakes are moving systematically in a particular direction, that can indicate fluid migration or stress transfer along a specific pathway. Another is whether the swarm includes any larger events that show the characteristic signatures of thrust faulting on the main plate interface, as opposed to the more varied fault mechanisms that tend to appear in volcanic or hydrothermal swarms. A third is whether deep tremor activity and shallow swarm activity are occurring simultaneously, which could suggest a connection between slow slip at depth and stress loading at shallower levels. The current swarm data includes elements that researchers consider worth examining closely. That is a careful way of saying something specific without overstating it. It means the pattern is not obviously benign, but is not clearly alarming either. It is what uncertainty looks like in real time, from the inside. This is where the communication challenge becomes most acute. If you report that researchers consider the pattern worth examining closely, that can sound alarming in a headline even though it describes a normal part of the scientific process. Researchers examine patterns closely. That is what science is. But in the context of Cascadia, close examination carries a weight that the same phrase would not carry in a different geological setting. There is another dimension to this story that rarely gets the attention it deserves, and it involves the network of monitoring instruments that we rely on to understand what is happening beneath the Pacific seafloor. The seismic monitoring network along the Cascadia margin is genuinely impressive in scope and has grown substantially over the past 2 decades. The Ocean Observatory's initiative has deployed instruments on the seafloor off the coast of Oregon and Washington that can detect very subtle seismic signals that would be invisible to land-based networks. The Pacific Northwest Seismic Network operates dozens of stations that provide high-quality real-time data. This monitoring infrastructure has transformed scientific understanding of the Cascadia system. But the offshore monitoring coverage, while better than it was, still has gaps. The most seismically critical zone of the Cascadia subduction zone is the locked interface between the 2 plates, which lies offshore under the ocean. Getting high-quality seismic data from that zone requires seafloor instruments, and seafloor instruments are expensive to deploy, maintain, and retrieve. The monitoring network provides good regional coverage, but there are sections of the plate interface where event locations and depths carry larger uncertainties than scientists would prefer. This matters for interpreting the current swarm, because some of the activity is occurring in areas where the depth estimates for individual earthquakes have higher uncertainty. Whether an earthquake is occurring at 10 kilometers depth or 25 kilometers depth makes a significant difference for determining whether it is happening on the main plate interface or in the overlying crust. Getting that distinction right requires either very dense station coverage or specific deployment of temporary instruments, both of which require time and resources. The United States Geological Survey and partner agencies are not sitting still. Additional monitoring resources are brought to bear when interesting swarm activity is detected. Portable seismometers can be deployed. Existing data archives are mined for comparison with current patterns. The scientific response is active even when the public communication is measured. What does all of this mean for the millions of people who live in the Pacific Northwest? The practical answer has not changed, and this is in some ways the most important thing to understand. Individual earthquake swarms come and go. The underlying hazard from the Cascadia subduction zone is persistent. It is there regardless of whether a swarm is occurring right now. A period with no significant swarm activity does not mean the hazard is lower. A period with elevated swarm activity does not necessarily mean the hazard is higher. The physics of the locked plate interface are being driven by processes that operate on timescales much longer than any single swarm event. What this means practically is that the appropriate response to the current swarm is not panic, but it is also not dismissal. The appropriate response is the same response that has been appropriate for decades: preparation. If you live in a coastal zone within the tsunami inundation area for a Cascadia event, you should know your evacuation route. You should know how to recognize the natural warning signs of a tsunami-genic earthquake. which include very strong and prolonged shaking and the sudden withdrawal of the sea from the beach. You should not wait for an official warning, because in some locations an official warning may not arrive before the first wave does. If you live inland in the Pacific Northwest, seismic retrofitting of older buildings, particularly unreinforced masonry structures, significantly reduces the risk of death and serious injury from strong shaking. Securing heavy furniture and objects that can fall and cause injury costs very little. Maintaining a supply of water and food for several days costs very little. These preparations are relevant whether or not any particular swarm is happening, because the hazard does not disappear between swarm episodes. The scientific community studying Cascadia is genuinely good at what it does. The researchers who have spent careers analysing the geological record of past ruptures, deploying instruments to track ongoing deformation, and modelling the physics of subduction zone behaviour have produced a body of work that is as thorough and honest as any in Earth science. They will continue monitoring the current swarm. They will produce better answers about what it means as the data accumulates, and they will communicate those answers through the channels they have available to them. But they are not going to issue a statement saying that a great earthquake is coming. They cannot say that because they do not know it. They know that one will come eventually, they do not know when. The current swarm does not change that fundamental uncertainty, even if it sharpens attention on the system for a period. What the swarm does, if nothing else, is serve as a reminder that the Pacific is not a passive ocean floor. It is an active geological system that has produced catastrophes in the human past and will produce them again. The question of when is genuinely open. The question of whether the Pacific Northwest and the communities along its coast are as prepared as they could be for that eventual event is one with a known answer, and the answer is not yet. The instruments are recording, the researchers are watching, the data is accumulating. And beneath several kilometres of cold Pacific water, two plates continue the grinding, relentless, accumulating process that has been underway since long before any human set foot on the North American continent. Whatever the current swarm ultimately turns out to be, a transient cluster or something more telling, it is a reminder that the Pacific floor does not sleep. It never has. And the people whose job it is to understand it are working right now to determine what it is trying to say. Let us go further back than 1700, because the geological record along this coastline is not a single entry. It is a long ledger, and each line in that ledger represents a catastrophe that happened to an area where no written history existed at the time to record it. Researchers who study coastal stratigraphy along the Pacific Northwest have developed techniques for reading past Cascadia ruptures out of the ground itself. The method involves looking at what are called buried marsh sequences. When a great earthquake occurs on a subduction zone, the coastal land can suddenly drop, sometimes by a metre or more, because the accumulated elastic strain in the overriding plate releases all at once and the land snaps back down. Where that happens, forests that were standing at or above the tide line are suddenly below it. They drown in salt water, their roots stay fixed in place, and over time sand washes in and buries them. What you end up with, centuries later, is a layer of dead root systems and drowned soil covered by marine sediment, sitting in the middle of what is now a meadow or a field, preserved underground like a message written by the earth to anyone patient enough to read it. These buried layers have been found at dozens of sites along the Pacific Northwest coast. Each one corresponds to a separate rupture event. Radiocarbon dating of organic material within the layers allows researchers to assign approximate ages to each event, and when you line up all those dates, a pattern emerges. The southern portion of the Cascadia subduction zone, the segment offshore from Northern California and Southern Oregon, tends to rupture more frequently and with somewhat less total energy than the full system. The full margin ruptures, the ones where the entire 1,000-kilometre contact surface fails simultaneously, happen less often but are dramatically more powerful. The 1700 event was full margin. The evidence shows that clearly. The land level change at coastal sites across the whole extent of the zone happened at the same time. The tsunami reached Japan. The shaking was felt across a region too large to be anything less than a complete rupture. Before that, there were other full margin events. The geological record suggests one sometime in the 14th century, another a few centuries before that, others before those. The intervals between full ruptures show considerable variability. Some were closer to 200 years apart, some were more than 500. This variability is not comforting, because it means you cannot simply count years and estimate timing from the recurrence interval alone. The system does not run on a clock, it runs on physics, and the physics involve more variables than the passage of time. One of those variables is something researchers have started examining more carefully in the past decade: the role of adjacent fault systems in altering the stress state on the main Cascadia interface. The Pacific Northwest is not simply the subduction zone and nothing else. The region is threaded with secondary faults, some well mapped and some still being characterized. The Seattle Fault runs directly beneath the city. The South Whidbey Island Fault is another major structure. Numerous smaller faults exist throughout western Washington and Oregon. These faults are not the source of the great earthquake risk in the way that the subduction zone is, but they can produce significant earthquakes in their own right, and the relationship between activity on these secondary faults and the stress state of the main interface is a subject of ongoing research. The concern is not that a secondary fault earthquake would trigger a subduction zone rupture in any simple mechanical sense. Faults do not work like dominoes where one falls and knocks over the next, but stress changes propagate through rock, and if a significant earthquake on a secondary fault redistributes stress in a way that brings a section of the locked interface closer to failure, the interaction could reduce whatever time remained before the next great rupture. Not dramatically, not in a way that changes decades into years, but potentially in a way that matters. This kind of stress interaction has been documented in other parts of the world. After large earthquakes in some regions, the pattern of subsequent seismicity on nearby faults shows changes consistent with Coulomb stress transfer, which is the mechanism by which failure on one fault alters the stress environment for adjacent faults. Cascadia researchers are applying these same analytical frameworks to their system, trying to understand how the secondary faults and the main interface influence each other over time. The current swarm is being examined through this lens as well. Some of the shallow crustal earthquakes in the swarm are occurring on or near known secondary structures. Understanding whether those events are loading or unloading stress on adjacent sections of the main interface is part of what makes the ongoing analysis genuinely complex. There is a component of this story that involves something happening not beneath the Pacific, but in the atmosphere above it, and the connection is more direct than it might initially sound. The Pacific Ocean is not a static reservoir. It is a dynamic system exchanging heat, moisture, and mass with the atmosphere continuously. One consequence of this exchange that most people do not think about is that the mass of water sitting above the seafloor at any given location is not constant. Ocean circulation patterns shift the distribution of water across the basin. Sea level variations, both regional and global, alter how much water sits above particular sections of the seafloor, and this matters for fault systems in a way that is subtle but geologically real. Water pressure acts on fault systems. This has been known since at least the 1960s, when it was demonstrated that deep injection of fluids at a Rocky Mountain waste disposal site triggered earthquakes on nearby faults. The mechanism involves fluid pressure reducing the effective normal stress on a fault plane, which makes it easier for the fault to slip. This same principle applies in a much more diffuse and gradual way to the effects of changes in the ocean water column above a subducting fault system. Researchers have documented correlations between periods of anomalously high or low sea level and variations in background seismicity rates in some subduction zones. The correlations are not perfect and the signal is buried under considerable noise, but they are detectable in the data when you analyze sufficiently long records. The Pacific has been experiencing unusual circulation patterns over the past several years, associated with shifts in large-scale ocean dynamics. These shifts affect sea level regionally. Whether those sea level changes have a measurable effect on the seismicity of the Cascadia system is something researchers are beginning to investigate, though this line of inquiry is at an early stage and the results are not yet definitive. The reason this matters is not that ocean circulation is going to trigger a Cascadia rupture in any direct or imminent sense. The stresses on that fault interface are far too large for ocean pressure fluctuations to be the deciding factor. But it matters because it illustrates something important about how complex and interconnected the system is. The ocean, the atmosphere, the solid earth beneath, the deep mantle below that, all of these are coupled to each other. They exchange energy and stress and mass on timescales ranging from hours to millions of years. Understanding any one of them in isolation gives you an incomplete picture of the behavior of the whole. The geophysicists and seismologists who study subduction zones are acutely aware of this complexity. It is part of why earthquake prediction in the specific sense of stating a time and magnitude in advance remains beyond current scientific capability, not because the physics are unknowable in principle, but because the system has more variables interacting on more timescales than any current model can fully capture. Let us move to something that does not often appear in coverage of Pacific seismicity, but that adds an important dimension to the story. In the years since the 2004 Indian Ocean earthquake and the 2011 Tohoku earthquake in Japan, the scientific understanding of the tsunami risk from large subduction zone events has been substantially revised upward in certain respects. Both of those events exceeded what had been considered the realistic maximum for their respective fault systems. The 2004 earthquake was larger than most models had predicted was possible in that particular subduction zone. The Tohoku earthquake produced tsunami run-up heights in some coastal locations that exceeded what local hazard maps had indicated was the credible maximum. In both cases, the physical evidence in the geological record showed that events of comparable or even greater magnitude had occurred in the distant past. The problem was not that the evidence was absent. The problem was that it had not been fully integrated into the operational risk assessments used for planning purposes. The lesson the scientific and emergency management communities took from both disasters was this: when the geological record shows that something has happened before, you treat it as the baseline for what can happen again, even if it exceeds your existing worst-case scenario. For Cascadia, that lesson has been applied, at least in the academic literature. The geological record shows full margin ruptures. The geological record shows that tsunamis from Cascadia events have reached the Japanese coast. The geological record shows coastal land level changes of a meter or more. Those data points are the basis for the current hazard assessments, and those assessments describe a scenario that by any reasonable measure represents one of the most consequential natural disasters that could occur on the North American continent in the foreseeable future. There is a specific number that tends to appear in discussions of Cascadia preparedness that requires some careful handling, because it can seem either alarming or falsely precise depending on how it is presented. The number comes from modelling work examining the probable casualties and displacement from a full margin Cascadia rupture combined with the resulting tsunami. The models produce estimates in the range of tens of thousands of fatalities in the worst scenarios, with hundreds of thousands of people displaced from their homes for extended periods. These estimates depend heavily on assumptions about the time of day the earthquake occurs, how successfully coastal residents respond to natural warning signs, how many people are in tsunami inundation zones at the moment of rupture, and how damaged infrastructure affects emergency response. The numbers are not predictions. They are scenario outputs from models built on physical and demographic data. But they are based on serious scientific work, and they are the kind of numbers that tend to concentrate the attention of anyone who sees them in the context of a region they know and care about. What they reveal, when you examine the assumptions behind them, is that the single most important factor determining casualty levels in the tsunami zone is not the size of the earthquake or the height of the waves. It is how many people successfully evacuate before the water arrives. The physics of the tsunami cannot be changed. The tsunami will arrive on some coastal sections within 15 to 20 minutes of the shaking stopping. But the response of the people in the path of the wave is a variable that can be changed through preparation, education, and infrastructure investment. Some coastal communities in the Pacific Northwest have made serious investments in tsunami preparedness. Vertical evacuation structures have been built in some locations, which are essentially reinforced platforms elevated high enough above the ground to be out of reach of expected wave heights. These structures are explicitly designed for the scenario where horizontal evacuation to high ground on foot is not possible in the available time. They represent a recognition that a portion of the population in some coastal communities will not be able to reach naturally elevated terrain before the wave arrives, whether because of mobility limitations, distance to high ground, or the disruption to road networks that the shaking itself will cause. Tribal communities along the Washington and Oregon coasts have maintained oral traditions describing the effects of past Cascadia events that are remarkably consistent with what the geological record shows. Some of those communities have integrated those traditional accounts into their contemporary emergency planning, treating the oral history not as mythology, but as genuine historical documentation of geological events. There is something both instructive and moving about the continuity of knowledge over 300 years, passed through spoken tradition across generations, describing a catastrophe that science only reconstructed from buried marshes and Japanese tsunami records in the latter half of the 20th century. The science and the oral history converge on the same event. That convergence is part of why coastal geologists take the traditional accounts seriously as a source of historical data. When independent lines of evidence point to the same conclusion, confidence in that conclusion increases, regardless of the medium in which the evidence is encoded. Now let us go somewhere else along the Pacific margin, because the story of what this ocean is doing is not limited to the Cascadia Zone and the Aleutians. The Pacific Ring of Fire is not a metaphor. It is a real, physical feature of the planet, a nearly continuous band of active tectonic margins encircling the Pacific Basin, where the oceanic crust is being subducted beneath surrounding continental plates. The ring includes the western coast of the Americas from Patagonia through Central America, Mexico, California, the Pacific Northwest, Alaska, the Aleutian Chain, the Kamchatka Peninsula, Japan, the Philippines, Indonesia, New Zealand, and numerous island arcs in between. At every point along that ring, similar processes are operating. Oceanic plate diving beneath continental or island arc crust, generating earthquakes and volcanoes, deforming the landscape. The Pacific is actually shrinking. The total area of the ocean basin is decreasing as the surrounding subduction zones consume the Pacific plate faster than new crust is being created at the mid-ocean spreading ridges. This is a geological scale trend, operating over tens of millions of years, with the eventual geological outcome being the continued reduction of the Pacific basin. The process is slow enough to be irrelevant on human timescales, but is worth naming because it contextualizes why the Ring of Fire is so active. You are watching, in very slow motion, a major ocean basin being consumed. Along the western margin of the Pacific, Japan sits directly above one of the most complex assemblages of subducting plates on the planet. The Japanese islands are being squeezed and deformed by multiple converging plates simultaneously. The 2011 Tohoku earthquake occurred on the fault where the Pacific plate subducts beneath the Eurasian plate off the northeastern coast of Japan. It produced a rupture roughly 500 kilometers long. The shaking caused damage across a wide swath of northeastern Honshu. The tsunami killed nearly 20,000 people. The waves overtopped protective seawalls that had been built to withstand a historical maximum wave height, because the actual wave exceeded that historical maximum. The monitoring and modelling capabilities of Japanese earth scientists had, in the years before 2011, begun to identify anomalous signals in some of the data from the Tohoku area. There was discussion in the Japanese seismological literature about the possibility of a larger-than-expected event in the region. But the operational hazard assessments that governed the design of the seawalls and the evacuation planning had not yet incorporated those concerns. The institutional inertia involved in revising engineering standards and hazard classifications is significant, and the scientific uncertainty around the anomalous signals was genuine. This is not a story about ignored warnings. It is a story about the difficulty of converting probabilistic scientific concern into action before an event occurs, especially when the event being contemplated is one that has no close historical precedent in the modern record. Japan has made extraordinary investments in earthquake and tsunami preparedness since 2011. The monitoring networks have been upgraded. The seawall systems along many coastal sections have been rebuilt or heightened. The evacuation signage and planning has been substantially revised. The country treats the memory of 2011 as an ongoing lesson, not a closed chapter, and the institutional response to that event is one of the more thorough national hazard preparedness efforts anywhere in the world. There is something instructive in the contrast between how Japan has responded to the lessons of 2011 and how the Pacific Northwest has responded to the lessons of the research on Cascadia. In both cases, the scientific knowledge of the hazard is well established and publicly known. The scale of institutional and infrastructure response, however, reflects a difference in immediacy. Japan experienced the event. The Pacific Northwest has studied the historical evidence of similar events. Experiencing a disaster generates a different kind of institutional motivation than studying the evidence that a future disaster is probable. This is a human limitation, not a scientific or political one. It reflects something true about how urgency is calibrated relative to direct experience versus probabilistic projection. Researchers who study disaster risk and public communication use the term availability bias to describe the tendency to assess risk based on how easily you can bring examples to mind. For communities in northeastern Japan, the memories of 2011 are vivid and immediate, which makes the assessment of tsunami risk intuitive and compelling. For communities in Portland or Seattle or the Oregon coast, the last great Cascadia event happened in 1700, and no living person has any direct experience of it. The risk assessment requires actively choosing to engage with evidence that has no direct emotional resonance in personal experience. This is one reason why the earthquake swarm currently being recorded in the Pacific is not a trivial news story, even if it turns out to be seismically benign. Every episode of elevated activity provides an opportunity to reconnect a population with an awareness that the hazard is real and present, not theoretical and remote. Whether that opportunity is taken depends on how the information is communicated and by whom. Let us talk about something that sits adjacent to all of this and that rarely receives the attention it deserves. The question of what happens to the Pacific Northwest critical lifelines when the shaking does occur, and why the answers to that question are considerably more sobering than most people appreciate. The Willamette Valley, running north-south through western Oregon between the Cascade and Coast Ranges, sits on sediment deposited over thousands of years. Much of that sediment is loose, saturated, and capable of undergoing liquefaction during strong shaking. Liquefaction is the process by which saturated granular material, when subjected to cyclic stress from earthquake waves, temporarily loses its solid characteristics and behaves more like a liquid. The ground quite literally flows. What that means for structures sitting on that ground ranges from settlement and tilting to complete foundation failure. A significant portion of Portland's infrastructure, including port facilities, wastewater treatment plants, and fuel storage terminals, sits on precisely this kind of liquefiable ground. The fuel storage terminal situation deserves particular attention because of what it means for post-earthquake recovery. The Portland area has a concentration of petroleum and natural gas storage facilities along the Willamette River waterfront. These facilities supply fuel not just to the Portland metropolitan area, but to communities across a wide region of Oregon and into parts of Washington and Idaho. If those facilities are damaged by shaking or by the ground deformation and flooding associated with liquefaction, the fuel supply disruption radiates far beyond the immediate earthquake zone. A modelling exercise conducted by the state of Oregon produced an assessment of this vulnerability that was published in a report generally known by the informal name the Resilience Plan. The report concluded that a full Cascadia rupture would very likely destroy or disable most of the fuel storage capacity along the Willamette River waterfront, and that restoring fuel supply to the region could take weeks to months depending on the extent of infrastructure damage and the condition of transportation routes needed to bring in supplies from elsewhere. Without fuel, emergency generators stop. Without emergency generators, hospitals and emergency communication systems lose power. Without functioning hospitals and emergency communication, the cascading effects on life safety extend well beyond the direct casualties from shaking and tsunami. The fuel supply vulnerability has been known since before the Resilience Plan was published. It has been the subject of government reports, media coverage, and community discussion. Addressing it comprehensively would require either hardening the existing facilities against seismic damage, which is technically demanding and extremely expensive, or developing alternative fuel distribution infrastructure that could function after the existing waterfront facilities fail, which requires substantial capital investment and long-term planning. Progress on both fronts has been slow. The reasons are a combination of cost, regulatory complexity, and the difficulty of sustaining political priority for a threat that has not materialized in the memory of anyone currently living. The bridge situation along the primary transportation corridors is similarly documented. Interstate 5 crosses the Columbia River between Portland and Vancouver, Washington, on bridges that were assessed in state engineering studies as unlikely to remain functional after a major Cascadia event. Without those crossings, north-south movement of personnel, supplies, and emergency equipment through the most heavily populated corridor of the Pacific Northwest becomes a vastly more complicated logistical problem. Interstate 90, connecting Seattle to eastern Washington, crosses on structures with their own seismic vulnerabilities. The networks of smaller bridges serving local communities throughout western Washington and Oregon represent thousands of separate structures with varying levels of seismic resistance. Bridge retrofitting programs have been underway in both states for decades, and significant improvements have been made. The prioritization of which bridges to retrofit first has been guided by modelling of which structures are most critical for post-earthquake mobility and which are most vulnerable to failure. This is genuinely useful work, but the total inventory of bridges in the likely shaking zone is large enough, and the retrofitting is expensive enough, that completion of a comprehensive upgrade program remains years away, even under the most optimistic scenarios for sustained funding. This is where the current conversation about earthquake swarms and Cascadia hazard intersects with questions of governance and public priority. The hazard is not a mystery, the specific vulnerabilities are not hidden, the necessary investments are, to a significant degree, known and costed. What is missing is not information. What is missing is the sustained political will to prioritize infrastructure resilience at the scale the hazard warrants, in the face of competing demands on public resources over the period of years required to make meaningful progress. Emergency managers who work on Cascadia preparedness understand this situation clearly. They have spent years developing nuanced communication strategies designed to convey genuine urgency without generating panic or what they call the crying wolf effect, in which repeated warnings that do not result in imminent disaster erode the credibility of future warnings. The challenge is real. The Cascadia hazard has been communicated as serious and imminent feeling for decades, without the event occurring, because the event is genuinely probable on a geological timescale that does not map neatly onto the human experience of urgency. There is an analogy that some researchers use when discussing this challenge, though they use it carefully because all analogies have limits. The analogy is to pandemic preparedness. The scientific community had been warning for years before 2020 that a pandemic of significant scale was a realistic probability, not a remote possibility. The probability assessments were based on solid epidemiological reasoning about the frequency and characteristics of novel pathogen emergence. The warnings were present in policy documents, academic literature, and even some public communications. What was missing was sustained institutional prioritization of pandemic preparedness at the scale those assessments implied was warranted. The event, when it arrived, validated the warnings, but also revealed that the gap between knowing a risk is real and preparing for it adequately is not automatically bridged by scientific knowledge alone. Cascadia researchers do not claim their situation is identical. The timescale is different. The type of event is different. But the structural challenge of translating probabilistic scientific knowledge into institutional preparedness before an event validates that knowledge is similar enough that the comparison has real explanatory power. Now let us shift perspective in a way that will initially seem like a departure from the Pacific story, but that is actually central to understanding it. The science of earthquake prediction has a complicated history, and it is worth spending some time on that history because it shapes how the current scientific community positions itself when discussing anomalous patterns like the current swarm. In the 1970s and early 1980s, there was a period of genuine scientific optimism about the possibility of developing reliable earthquake prediction methods. Researchers were finding patterns in pre-earthquake seismicity, in changes to ground deformation, in variations in the electrical and magnetic properties of rocks, that seemed to suggest precursor signals might be identifiable before large earthquakes. Several countries, including the United States, the Soviet Union, China, and Japan, invested substantially in earthquake prediction research programs. In 1976, a major earthquake struck the city of Tangshan in northern China, killing several 100,000 people. In the months before the Tangshan earthquake, there had been elevated animal behavior anomalies reported in some surrounding areas, as well as some unusual seismic activity. None of it was sufficient to generate an official prediction. The earthquake was not predicted, and the casualties were catastrophic. In the aftermath, some researchers argued that the precursor signals had been there but not recognized in time. Others argued that the signals were ambiguous and that hindsight was creating the appearance of a pattern that was not predictive in any rigorous sense. In 1989, the Loma Prieta earthquake struck the San Francisco Bay Area. In the weeks before the earthquake, a scientist named Hartley Steen had made a statement suggesting that a significant earthquake was possible in the area based on patterns he was observing. The earthquake occurred shortly after. The prediction was not specific enough in time, location, or magnitude to be operationally useful, but the coincidence generated attention. It also generated a great deal of subsequent analysis trying to determine whether the pattern Stein had identified was genuinely predictive or coincidental. The careful, rigorous analysis that followed both of these cases, and many others, led the scientific community to a conclusion that was both honest and sobering. Earthquake prediction, in the specific operational sense meaning a statement of time, location, and magnitude specific enough to justify mass evacuation, and sufficient to allow emergency management action, has not yet been demonstrated to be possible with current methods. The precursor signals that have been identified in some cases are either too ambiguous to distinguish from noise, too inconsistent across different earthquakes of comparable type, or too spatially imprecise to be useful for targeted warnings. This conclusion is not permanent. Science advances. But it represents the current state of knowledge, and the scientific community is explicit about it, partly because the alternative, allowing speculation about prediction capabilities to outrun the actual evidence, creates real risks. False predictions of major earthquakes can cause evacuations that are themselves harmful and that erode trust in future warnings. The 1976 prediction of an earthquake in the Palmdale area of California that did not materialize, a prediction that received national media attention, generated enough damage to scientific credibility that it influenced how researchers communicated probabilistic concerns for years afterward. This history is the reason that when seismologists discuss the current Pacific swarm, they are careful to avoid language that implies prediction capability. They are not being evasive, they are being accurate about what the current state of science actually allows them to say. The patterns are interesting. The patterns are being studied. The patterns have not yet been deciphered in a way that allows a statement about whether a large earthquake will or will not follow. That is the honest position. And it is worth understanding that this position, while limiting in some ways, is also protective. A scientific community that cried wolf would eventually be ignored at precisely the moment when it had something genuinely important to say. Let us go underwater now, not just beneath the Pacific in a general sense, but to the actual sea floor along the Cascadia margin, because the physical environment where the most consequential geological processes are happening is genuinely strange and it deserves more than a passing reference. The Cascadia subduction zone's locked interface sits under kilometers of cold, pressurized seawater. The seafloor in the area where the two plates make contact is under pressures that would instantly crush any unprotected human being. The temperatures are just a few degrees above freezing, and yet the geological processes happening at those depths are among the most energetically significant on the planet's surface. The incoming Juan de Fuca plate is not a smooth, uniform slab of rock. It has topography. There are underwater mountains called seamounts embedded in the plate that are being carried along with the plate toward the subduction zone and eventually dragged beneath the continent. As these seamounts arrive at the trench and begin to be subducted, they interact mechanically with the overlying plate in ways that are not fully understood, but that appear to influence the frictional properties of the locked interface in their vicinity. There is an area off the coast of central Oregon where researchers have identified what they call the Newport embayment, a section of the Juan de Fuca plate that appears to have different mechanical characteristics than the surrounding regions. The embayment is thought to influence the way stress accumulates and releases along that segment of the locked zone, whether it acts as a barrier that would stop a rupture from propagating through, or as an asperity that concentrates stress and fails dramatically when it eventually gives way, is something researchers have been trying to determine for years. The answer matters significantly for how a future Cascadia rupture might unfold, because the extent of the rupture along the plate boundary determines the total energy released and the pattern of tsunami generation. The seafloor offshore the Pacific Northwest has been mapped in increasing detail over the past 2 decades using multi-beam sonar systems. This mapping has revealed that the accretionary prism, the wedge of sediment that has been scraped off the subducting plate and piled up against the continent over millions of years, has a complex internal structure with faults and ridges that record the history of past deformation. Reading those structures provides information about where deformation has been concentrated in the past, which in turn informs estimates of where it is likely to be concentrated in future events. There are also methane seep communities scattered across the Cascadia seafloor. These are ecosystems that derive their energy not from sunlight, but from chemosynthesis using the methane that seeps up through the seafloor from the sediment below. These communities exist because the accretionary sediments contain large amounts of organic material that has been partially broken down into methane over geological time. The methane is held in the sediment in a form called methane hydrate, a crystalline ice-like structure where methane molecules are trapped inside cages of water, molecules under the cold, high-pressure conditions of the deep sea floor. The methane hydrate deposits along the Cascadia margin are substantial. They have been studied both for their scientific interest as records of past climate and biological activity, and for their potential as an energy resource. But they have also been studied for their mechanical implications for the seafloor and the subduction zone. Methane hydrates are stable at the temperatures and pressures found in deep water, but they are sensitive to both temperature and pressure changes. If bottom water temperatures warm, or if the pressure above them decreases, which can happen when sea level drops or when the seafloor experiences stress changes from seismic activity, the hydrates can dissociate, converting from solid crystalline structures back into free methane gas and water. This dissociation weakens the sediment in which the hydrates are embedded, because the hydrate crystals were contributing to the mechanical strength of the sediment. The relationship between earthquake activity and hydrate dissociation along the Cascadia margin is a subject of active research. There is evidence from acoustic imaging of the seafloor that some areas show elevated methane seepage following episodes of seismic activity, which is consistent with the idea that the shaking and stress changes associated with earthquakes are triggering dissociation. Whether this is a meaningful feedback loop within the subduction system, where earthquakes cause hydrate dissociation, which alters the mechanical properties of the sediment, which in turn influences subsequent fault behavior, is genuinely uncertain. But the possibility is interesting enough that it has generated serious scientific attention. This is a good example of why the current scientific understanding of the Cascadia system resists easy summarization. The system involves not just the two main plates and the main locked interface, but a whole cascade of interacting physical and chemical processes happening across a range of depths and length scales. You have the deep mantle dynamics that are ultimately driving the plate motion. You have the mechanical behavior of the plates themselves. You have the frictional properties of the locked interface, which depend on temperature, pressure, fluid content, and the mineralogy of the fault zone rocks. You have the sediment wedge with its internal faults and its hydrate deposits. You have the volcanic plumbing systems fed by the subduction process. You have the secondary faults in the overlying continent. You have the ocean water column above with its pressure and temperature gradients. All of these are interacting continuously, and the seismicity we observe at the surface is the integrated result of all of that interaction. The swarm being currently recorded is a perturbation in that system. Whether it is a meaningful perturbation or a transient fluctuation that will decay without consequences is the question that cannot yet be answered, and understanding why it cannot yet be answered requires appreciating the full complexity of the system, rather than expecting a simple input-output relationship. Let us talk about what a future Cascadia rupture would look like from the ground level, because the abstract language of geology and seismology can obscure the human reality of what these numbers and mechanisms actually represent. The shaking from a full margin Cascadia rupture, a magnitude 9 or greater event, would begin as a deep rolling sensation that rapidly intensifies. People in the affected area, which would include essentially all of Western Oregon and Western Washington, the Oregon coast, the Puget Sound region, and extending into British Columbia, would experience shaking lasting somewhere between 3 and 5 minutes. This is not an earthquake that shakes for 30 seconds and then stops. It is several minutes of sustained, violent ground motion that would make standing, walking, or taking purposeful action extremely difficult for most people. The duration matters enormously for structural damage. Buildings that might survive a shorter but equally intense shaking event accumulate cumulative damage over the extended duration of a magnitude 9. Older unreinforced masonry structures which still exist throughout much of the urban Pacific Northwest would be at very high risk of partial or complete collapse. Concrete buildings constructed before modern seismic codes were adopted in the 1970s and 80s would face serious risks as well. After the shaking stops, people in coastal zones would have a decision to make very quickly. The natural warning signs of a tsunamigenic earthquake are the shaking itself and the possible withdrawal of the sea from the beach. Anyone who feels very strong shaking lasting more than 20 seconds near the coast should immediately move to high ground without waiting for an official warning. This is not a precautionary overreaction. It is the behaviour that the physics of tsunami generation require for survival in the fastest arriving wave zones. People further inland would face a different situation. The immediate life safety threat for most of them would be the shaking itself. After the shaking stops, the problems would shift to a different set of challenges. Damaged or destroyed homes, disrupted utilities, blocked roads, and the beginnings of what would become a prolonged regional disruption. The emergency response to a full Cascadia rupture would be unlike anything experienced in the continental United States in the modern era. The affected area would be too large for mutual aid from adjacent regions to fill the gap quickly, because adjacent regions would themselves be in the shaking zone. The primary north-south transportation corridors would likely be compromised at multiple points. Aviation, which is the fastest means of moving personnel and supplies, would face challenges from airport damage and the sheer scale of demand relative to available capacity. Federal emergency response systems are designed with the assumption that a severely impacted area can receive assistance from surrounding regions that are not similarly impacted. The Cascadia rupture scenario challenges that assumption. The impacted area is large enough that the outer ring of adjacent regions, eastern Washington, eastern Oregon, Idaho, northern California, would be partially impacted as well, reducing their capacity to serve as fully functional staging areas. This means that the initial period of response, the first days and possibly first week or two, would be primarily a function of local and state resources that survived the event, supplemented by federal resources that can be moved in from regions far enough away to be unaffected. The implication is that individual and community preparedness matters more in the Cascadia scenario than in many other disaster scenarios, precisely because the gap between demand and available response capacity would be larger and last longer. Communities that have water reserves, food supplies, functioning neighbourhood communication networks, and basic medical capability that survives the shaking will be far better positioned in the initial post-event period than communities that have relied entirely on being able to call for help and have it arrive quickly. This is not a political statement about the role of government. It is a practical observation about the physics and logistics of responding to a very large-scale, regional disaster. The government response will come, and it will be substantial, but in the first 72 hours, the communities that have done the work of local preparedness will have dramatically better outcomes than those that have not. There is something else that deserves mention here, which is the reality of what happens to social networks and community cohesion after major disasters, because the research on this topic contains some findings that are both surprising and genuinely important for how people approach individual and community preparedness. Disasters are not uniformly destructive to social bonds. In many documented cases, significant natural disasters have produced periods of pronounced community solidarity and cooperation in the immediate aftermath. People help each other in ways that can seem inconsistent with the competitive and individualistic behavioral norms of normal times. Neighbours who had never spoken to each other before an earthquake share water, help each other dig out, provide mutual comfort. Communities that had persistent divisions and tensions find temporary common ground in shared crisis. This phenomenon has been documented in disaster sociology research, and it has practical implications. It suggests that pre-event investment in community networks, in knowing your neighbours and being known by them, is not just social nicety, it is infrastructure. The person who comes to check on you after the earthquake is as valuable as the emergency generator, and the social network that allows that person to find you and help you is built in normal times, not in crisis. The research also shows, however, that this period of elevated prosocial behaviour is temporary, and that communities with pre-existing strong social ties maintain cooperative behaviour longer and more effectively than communities that were more fragmented before the disaster. This is another argument for the kind of community-level preparedness work that involves actually spending time with people in your geographic community before any disaster occurs. The Pacific is not the only ocean sitting above an active and consequential geological system, but it is the largest, and the scale of what its margins are capable of producing is without parallel in the rest of the planet's ocean basins. There is a reason that the Ring of Fire encircles the Pacific specifically. The Pacific Basin is an old oceanic plate, and old oceanic plates are cold and dense, which makes them subduct readily. The rapid subduction of cold, dense Pacific material into the surrounding trenches is what generates the volcanic chains and the great earthquake zones that define the margins of this ocean. In the context of geological time, the current period of human civilization sits within a relatively quiescent period for some of the Pacific's most active systems. Quiescent does not mean inactive. It means active at a level below the maximum that the geological record shows is possible. The geological record for every major subduction zone along the Ring of Fire includes events larger than the historical maximum recorded in the modern instrumental record. This is not surprising. The modern instrumental record spans at most a few hundred years. The geological record spans thousands or tens of thousands of years. Over longer time periods, more extreme events have the opportunity to occur. What this means in practical terms is that the hazard assessments built from historical records of the modern era systematically underestimate the potential maximum for most seismic systems. The Cascadia system has been studied well enough that the geological record has been incorporated into the hazard assessments, which is why those assessments include the full margin rupture scenario. But for many other subduction systems around the Pacific, the geological record of past events has been less thoroughly examined, and the hazard assessments may be based more heavily on the shorter historical record. This is not an indictment of anyone's methodology. The geological investigation of past great earthquakes is genuinely difficult and expensive work. But it is a reason to treat current hazard assessments with some humility about the completeness of the underlying evidence. Let us return to something closer to home. There is a specific population in the Pacific Northwest whose situation in the context of Cascadia preparedness deserves particular attention: the population of students and workers who are present in older school and office buildings throughout western Washington and Oregon during the day. Earthquakes do not choose their timing, but the distribution of vulnerable buildings in the urban Pacific Northwest means that the time of day when a great rupture occurs will have an enormous influence on casualties. School buildings in the Pacific Northwest represent a particular concern. Many schools, particularly older ones built before modern seismic codes were adopted, have been assessed as highly vulnerable to structural failure in a major earthquake. States and school districts have known about this vulnerability for years. Retrofit programs have been implemented for some buildings, but the total inventory of potentially vulnerable school buildings is large, and the cost of comprehensive seismic upgrades is substantial. The situation is similar for commercial buildings, government buildings, and hospitals in the affected region. The hospital situation is particularly consequential because hospitals are precisely the facilities whose function is most critical in the immediate aftermath of a major earthquake. A hospital that is itself damaged by the shaking and unable to operate is a double loss, both a casualty producer and a removed resource for treating casualties. Oregon has passed legislation requiring the seismic assessment of hospitals and establishing timelines for upgrading or replacing hospitals that do not meet modern seismic performance standards. Progress has been made, but the timeline for full compliance extends years into the future, and the Cascadia rupture is not interested in waiting for regulatory timelines. There is something that the current swarm does regardless of what it ultimately represents in terms of seismic significance, and it is this: it creates a window of heightened attention during which the information about Cascadia hazard, preparedness gaps, and individual and community actions that can reduce risk is more likely to be sought and absorbed than at other times. This is not a cynical observation. It is an observation about how human attention works, and it is the reason that communicating clearly about these topics during periods of elevated awareness is valuable, even when the current specific activity turns out to be benign. People who look up information about earthquake preparedness because they heard about the Pacific swarm and became curious will find that information is available. They will find that the recommended supplies, water, food, medications, first aid materials, for several days are not expensive and do not require significant logistical effort to assemble. They will find that knowing their evacuation route if they live in a tsunami zone costs nothing. They will find that checking on the seismic status of their building and understanding what retrofitting options exist if their building is vulnerable is information that is available from local jurisdictions and from professional engineers. The information is there. The question is whether people act on it before the urgency of the moment fades. The seismologists who are watching the current swarm are not catastrophists. They are careful scientists who are precise about what they know and what they do not know. and who understand that both over-alarm and under-alarm carry real costs. They are doing their jobs with the instruments and methods available to them. They will have more to say about this swarm in weeks and months than they can say right now. And they are watching not just this swarm, but the Cascadia system as a whole, continuously, as they have been for decades. What they see is a geological system that is alive in the most literal sense, in which vast forces are continuously operating, in which the accumulated strain energy in the locked plate interface is real and measurable, in which the uncertainty about the timing of the next great rupture is genuine, but does not make the hazard less real, or the preparedness work less necessary. The ocean above all of this does not reveal what is happening at its floor. The surface looks the same today as it did yesterday. The cold water presses down on the silently accumulating stress of two colliding continental plates with the same indifference it always has. The seamounts roll slowly toward the trench. The tremor episodes send their quiet signal through the deep rock. The locked interface holds, as it has held for the 300 years since it last gave way, accumulating the elastic energy that will eventually, on a timescale that may be long or may be short by human reckoning, release in an instant. The instruments detect the small things. The small things are being recorded and analysed by people who have devoted their careers to understanding this system. And the small things, even when they turn out to mean nothing in isolation, are part of the continuous process by which science builds a more complete picture of a geological environment that matters enormously to the millions of people who have built their lives above it. The Pacific is not a threat to be frightened of in the sense that would make day-to-day life impossible. It is a fact to be understood, prepared for, and integrated into how individuals and communities think about the landscape they inhabit. The plate boundaries are not going to move because we worry about them, or because we stop thinking about them. They will do what the physics requires them to do, on the timescale the physics determines, without any reference to human preference or readiness. What is within human agency is the work of preparation. The water stored, the family plan discussed, the evacuation route walked, the building assessed, the community network built, the local emergency manager's guidance read and integrated. These things are within reach of any individual in the affected region, and they represent the difference between a disaster that is terrible and a disaster that is catastrophic. The two outcomes are not equal, and the distance between them is not determined by the earthquake. It is determined by what people do before it arrives. The swarm will continue to be monitored. The data will continue to accumulate. The researchers will continue to work through what the patterns mean. And the Pacific seafloor will continue doing what it has always done, relentlessly, quietly, in the dark, cold water far below the reach of any human concern. That is the story the current data is telling, to those who have the instruments to hear it, and the patience to listen carefully before speaking.